Hello, welcome to Cpp.chat, the #1 element in a zero-based array of podcasts, sorted chronologically, for C++ developers by C++ developers. Before we continue, as usual, I'd like my fellow host John to read this week's disclaimer.
Thank you, Phil. Cpp.chat Moving and Relocation Guide provides this website as a service. While the information contained within the website is periodically updated, no guarantee is given that the information provided in this website is correct, complete, and/or up to date. The materials contained on this website are provided for general information purposes only and do not constitute legal or other professional advice on any subject matter. Cpp.chat Moving and Relocation Guide does not accept any responsibility for any loss which may arise from reliance on information contained on this site. So, thank you. We have a couple of guests that I'm excited about having. We've had them both on before, and we know it's going to be a great discussion. Arthur O'Dwyer is the author of Mastering the C++ 17 STL, and he runs the Bay Area C++ user group. Arthur is also presenting and giving a class at CPPCon 2018. So, Arthur, how do you feel about the fact that that's only about 5 weeks away? Are you excited about that, or are you terrified about that?
Both. It'll be very different from last year. I'm giving the exact same class, but last year it was all new material. This year it's all 1 year old material. I'm gonna have to review my slides and everything. It's gonna be very different. That's a very different experience, at least for me. Same experience for everyone else, though. It's gonna be great.
Okay, that sounds fun. So Howard Hinnant is kind of tough for me to introduce, because if I told you how much I love and respect this guy, I'd embarrass us both. Howard currently works at Ripple, but has spent many years as a standard library maintainer and created libc++, the Clang standard library implementation from scratch. He also served as chair of the library working group on the standard committee for many years. So Howard, do you miss working on libc++, or are you glad it's no longer your problem?
Yes and yes. Thank you for having me on the show. I really enjoyed working on libc++ as a labor of love. There were some parts of it that I found frustrating to work on. I think ABI stability or ABI breakage was probably one of the things that I was worst at and most guilty of, and it's a problem I'm glad I don't have to deal with anymore. Good luck, Marshall. And he's doing a great job of it. Marshall's been taking care of libc++ for 4 years now, over 4 years, and doing a fantastic job. And I understand he's set to continue doing that for the foreseeable future.
Yeah, there is a big announcement concerning Marshall coming out, but I'm just gonna tease you with that. Stay tuned. I don't think it's very far away, but big announcement from Marshall. Anyway,
I'm not saying anything.
Okay. So I think it was the last time you were on, I asked you about Thomas Geffs and his top 10% log, where he did this interesting shootout where he compared partial sort with nth element followed by a full sort. And the takeaway you have from reading his blog is that you shouldn't use partial sort, and it's not because it's badly specified, but because the algorithm chosen to implement it is incorrect. He kind of implies that if partial sort was implemented as an nth element followed by a full sort, it would be dramatically better. So I hit you with that. But today I'm going to ask you a different question. Unless you want to comment on that, I'm going to ask you a different question. You gave a talk a long time ago, while you were still at Apple, I think, talking about libc++ and the sorting algorithm that was used in libc++, and you described it as essentially discovering and taking advantage of subsequences of your data that's already sorted. And so, but I don't think in your talk you actually talked about what the algorithm was or how you were doing that. You just said, this is what we're doing now. So can you tip your hand a little bit and talk about what's going on there?
Sure, absolutely. After all, the algorithm's open source, so anybody's welcome to or able to go in there and take a look at it. And it's actually more than just detecting whether a subsequence is already sorted. It's detecting whether it's actually detecting patterns. Like, it'll also work very fast on a reverse sorted array. Even though none of a reverse sorted array is sorted, it's really fast on it.
So
And
isn't that one of the things that's kind of like quick sort, which is kind of the fastest sort, but does very badly if you happen to be completely reverse sorted initially, right?
It depends on how you partition it. It can be if you pick the wrong partition. Yes.
Because my understanding is that the way that sort is implemented is basically quick sort, except if it turns out to be in this pathological situation, then we switch over to heap sort, because heap sort, although not as efficient generally, has better worst time performance.
Right. And that's actually a bug in the libc++ sort, is that it's not doing that switch to heap sort when things go south. But the probability that it's going to go south is extremely low in the wild, but you can write a test to force it to do so. And actually, that may have been fixed in the last 4 years. That was a bug in the library when I left 4 years ago, and I don't know whether it's been fixed or not.
Well, we need to drag Marshall on and.
It should be a fairly easy bug to fix, because you just, heap sorts there in the algorithm in the library, and you just need to detect that you've recursed too deeply and switch, and just bail out and call the other algorithm.
Okay, so tell us
by intro sort, or is intro sort a different thing?
Oh, intro sort, gosh.
I think that is what intro sort is. Intro sort is starting with quick sort and switching to heap sort when you detect the problem. That's my understanding of what that term means.
Yeah, I believe you're right. I'd forgotten that. It's been too many years since I've been looking at sort. But if I go back and describe what's going on, the libc++ sort is a quick sort. It's just a modified quick sort. It initially is doing either a partition of 3 or partition of 5, depending on how big the array is. And during the partitioning process, it counts how many times it swaps elements. And if it does a partition and discovers that it gets through the entire partition and hasn't swapped any elements, then it'll say, maybe this is already sorted. And at that point, it'll do an insertion sort over that range. Now, the cool thing about his insertion sort is that if you insertion sort on an already sorted range, it's an order in process. It's very fast. Whereas other algorithms are not so great on pre-sorted data. But it won't do an entire insertion sort. During the insertion sort, it'll count how many inserts it makes. And there's some heuristic in there about if it makes too many inserts during the insertion sort, it'll just bail halfway through the insertion sort and pop back out to the quick sort. And so you've got this thing that's occasionally trying an insertion sort on sub-ranges. And if you're nearly sorted or already sorted, then you can just, that part of the job is done and you never come back to it. Or you fail and you go back to the quick sort and it continues recursing down just like a quick sort. Again, trying to detect as it gets to smaller and smaller ranges, eventually you'll get down to, very few elements that happen to be sorted, and you then insertion sort them, and yes, everything's fine, and you pop back out. So what this does is, for example, imagine you had a reverse sorted range that you put into this algorithm. You go in and you partition it, and you swap every single element in that reverse range. So you're just doing a normal quick sort. Then you subdivide, and you apply quick sort to the first half and quick sort to the second half. Now, in this instance, your first half and your second half are already sorted just because of the swapping that you did in the first partition. And so during this second stage phase, the libc++ is going to detect, the first half is already sorted. So that's very quick. And then it's going to detect again that the second half is already sorted. So you're only going to recurse down like 2 levels for reverse sorted range. So it gets executed very quickly.
Wow.
And that same reasoning applies to arbitrarily other patterns.
Where it just finds it in the code.
Yeah. And so, the worst case scenario is actually a perfectly random sorted, a randomized sequence where there are no patterns.
Right. So this is one of the questions I'd ask you with your hat on as a standard library developer. How do you have you have to, because you're doing the standard library, you have to make no assumptions at all about the data you're given, right? So you can't say, well, data tends to have runs of sorted data in it. Well, maybe in some applications, maybe in other applications not. I mean,
I would say your premise isn't quite true. I have to assume that there's no patterns in there for a worst case reasonably performing scenario. But I'm also allowed, and it's even to an implementer's advantage to say, yeah, but in the real world, often you're in cases where you do have lots of patterns. For example, it's common to sort a bunch of things and then do some more work and append some stuff to the end of it and then resort your entire range. And that's the sort of application that comes up all the time in the wild. And libc++ will do very well there because you've already got a big part of your thing that's already sorted.
Okay. All right. Well, thanks a lot. I appreciate a little detour into sorting here. I think
Probably
we have
more than anybody ever wanted to know.
No. I think that I hope that the software engineers are fascinated by sorting. I hope that
I certainly am. I certainly am.
So we have some announcements, conference announcements. Do you want to take? Because I think you have the biggest announcement, Phil.
I believe so. It's pretty big for me. So last week, C++ on C, we opened the registrations for early bird tickets. That's still open till the end of the month. As of today, I have pushed out a campaign where if you send out a tweet saying what you'd be looking forward to in C++ on C, you'll be entered into a draw for a free ticket. So all the details are on the current news page on the cpp.c.uk. Put a link in the show notes. That's going to run until next Friday. So I have to be a little bit careful here because judged on recent performance, this podcast may not be out before then, but I'm really going to try and get back on top of it this time around. So hopefully I have at least a few days to get that in. For those listening live, you may have an advantage there.
Yes, get those tweets flying. We have my news for CPPCon is that our hotel blocks are expiring literally within a few days. So if you have not booked your hotel, absolutely you want to do that right away. And the other news is not really news. I'm just teasing people. It looks like we are going to have a field trip. I was thinking we wouldn't have one this year because we had plans for one and those plans fell through and there just wasn't time before registration to fix it. However, we have a few volunteers that said, we got to have a field trip. And so they've taken it upon themselves and I'm kind of excited at what they've gone. I never get to go on it because I'm always working to prepare the conference. But this one, I really kind of want to go on, but that's because I'm a sucker for this. But anyway, so what else is going on? Pacific++ has just put up their schedule. And so you can see what their talks are. And let's see, who are we missing? ADC still has tickets open.
And Meeting C++ and Meeting Embedded.
Yeah, and they've released their schedule, but I think they had already done that for last. Okay. All right. So I think we're ready to tackle our main topic. And on this one, I think Arthur is the big troublemaker. Arthur, what have you gotten us into here?
Well, it's something that's been tried a lot of times before, right? Object relocation. So sort of, we have malloc and free, and we have realloc in C, and then in C++ we have new and delete, and we don't have any sort of renew or realloc type thing in the language, and we also can't really get it in the library, like in vector. If I have a vector of std strings, for example, and I want to reallocate it and take that whole array of strings and put it somewhere else. In C++03, I had to actually make copies of all of them and then destroy the originals. And we've done better, thanks to people like Howard in C++11, that now we can move all of them and then destroy the originals. But even that is slower than it needs to be. Let
me stop you real quick right there. So vector cannot be implemented using malloc and realloc because moving all the bytes, the values of all the bytes, which is what realloc will do, right? I mean, if I realloc, ask for more memory, if it can't add the memory in place, which is the usual case, then it has to create a new buffer and move everything over. But because this is a C library, it's just going to move bytes. It doesn't know anything about constructors and destructors, right? So that's why we can't use realloc as an implementation in the library.
Right. Well, that's why the language says you can't use it, right? But we know, you and I know, that in fact, for std string, you could just move the bytes and it would actually work great, right? I mean,
sure.
You know, pointers or even with the small string optimization, it's just got the characters right there. I think
std string's not really unique in that situation.
Most things, not all things, and it's possible to implement a std string with the, you know, if you had a small string optimization where you had a pointer that sometimes pointed to the heap and then sometimes it pointed to within the object itself.
Right.
Then if you copied all the bytes to somewhere else, that pointer would now point, you know, into garbage. So
any object that has a pointer into itself is a real problem for anything like this. And having a pointer into yourself is completely legal. Any object could, in fact, do that.
That's right. So it would be really nice if things like vector could do this, but they can't at the moment because they can't do it generally because there are objects with pointers into themselves. libc++'s std function is an example of that. Std function actually does do this small object optimization with a pointer into itself. And so if you move a std function from one place to the other, it's not going to work. Another really common example would be std list, right? Because std list is sort of a big circular doubly linked list. And so it has a pointer coming into it from outside, from the tail of the list. There's a next pointer that goes to the list and a pre pointer that comes back, right? And so if you move a std list, then you break those incoming pointers. They point to garbage. So there are. You mean
the head and tail item are pointing into the body of the list item.
Right. You'd be able to iterate, if you iterated over this list, you would be able to get into the list just fine and go through all of the elements. And then the very last element, you'd take its next pointer and you wouldn't get the actual end of the list, you would get garbage, right?
Except on Visual Studio.
Does Visual Studio do the heap allocation?
Yeah, they don't have the embedded node like GCC and libc++.
Oh.
Yeah, I have investigated libc++ very heavily, and a little bit of std C++, and not really at all of MSVC to see how they do the different STL containers.
I haven't personally looked at the code. I get everything from Rumor.
It's the best source.
But that's what makes the current situation so, frustrating, right? Is that we know that memcopy often does the right thing for a certain subset of types, but
a large subset.
Yeah, but unfortunately, we can't even name them because you can't even say like, well, it works for, list, right? If you're on MSVC, it does work for list. If you're on GCC, if you're on, libstd C++, it doesn't work for list. And so a portable program has no way of, figuring this out. And if you look at existing libraries like Folly and EASTL, Folly in particular I've been looking at recently, it has this concept that uses it in FB vector. And it basically has an invariant that you're not allowed to put anything into the vector that doesn't work this way, because they just unconditionally memcopy things.
Oh, wow. Folly is Facebook's library, which they've now open sourced.
Right. And so if you're going to put anything into an FB vector, you have to warrant to the vector class that, yes, this thing is trivially relocatable. Or they just, I think they call it just relocatable. But so that means you can't have an FB vector of things like std string by default. Now, it turns out you can, right? Because that would be horrible if you couldn't put a string in a vector. So what they do is they have a hard-coded list of, here are the types that the implementers have decided are relocatable. And they just have a big whitelist of like std string, that's okay. Std vector, that's okay. Unique footer, that's okay. and they just go down this whitelist. And the problem is that
is that enforced at compile time? Is that what they do?
What's that?
I said, is that enforced at compile time?
Yes. Yeah, and then it'll static assert if you try to put something in that isn't on the whitelist and isn't trivially copyable. And you have ways you can add things to the whitelist yourself. You can warrant that you just make a specialization of a template of a type trait to say, I guarantee that my thing is going to be okay.
Right.
But the problem is someone has to go make that whitelist. Someone has to say, you know what, std string is okay. And it turns out, well, sometimes it is and sometimes it isn't. Right? Or, they had on their std list is okay, and no, it's not. I guess on MSVC it would be, and then on GCC it wouldn't be. And so maintaining that list of what types are safe and what types aren't is quite burdensome and quite a source of bugs.
But worth it because of the performance we get, right? I mean, this is a non-trivial performance impact to be able to do this. You've done some benchmarking along that lines, right?
Yeah, my C++ Now talk from C++ Now 2018. I gave a talk called The Best Type Traits C++ Doesn't Have. And I talked about 3 different things, but the first one that I talked about was this concept of just having some sort of type trait that you could ask, is this type safe in this way?
Which you're calling trivially relocatable.
Which I'm calling trivially relocatable.
I watched that talk last night. Very nice job.
Thank you. And it had, of course, very impressive benchmarks. But of course, that's because I was benchmarking things like, the time it takes to resize a vector, right? Ignoring all of the actual putting things in the vector and what else you're doing.
I remember Howard once telling me that the wonderful thing about move semantics is that you can create benchmarks of any arbitrary performance speed up that you want.
Yep.
Just make it nastier and it'll go faster.
Yeah, right.
But after giving that talk, that talk was really focused on the vector resizing application. And you might say, well, no, I don't normally just resize my vectors, right? I only do that geometrically often, right? Not very often in a big program. But I'm doing a lot of inserting. I'm sorting, right? We were just talking about sorting. But it turns out that this could actually speed up sorting as well, right? Because what is sorting? It's a bunch of swaps, right? And so if I make swap faster, then I can make this faster. And so in the standard library, basically every STL container, every unique putter, all that always has to overload swap. They have to provide a swap function because the default swap, the template, the unconstrained template would not be very fast because it would have to do a move construct and a move assign, and a destroy. Or, yeah, a destroy the temporary.
So in other words, every time we do a move, in a classic situation where we have a pointer to something that we own, which is where move makes sense, right? Because now instead of copying a buffer, we're just going to copy the move, the pointer. However, what we have to do is we have to go to the source and we have to zero out the source pointer because its destructor will be called. And when it is, it's going to wipe out the buffer that we've taken ownership of with our move. And what you're pointing out is that we're doing 2 things there. One is we're setting that pointer to 0. And the only reason we're setting the pointer to 0 is so that when the destructor is called, it doesn't delete that allocation. And so if we could somehow tell the compiler, don't bother setting the pointer to 0, and then don't bother running the destructor, then we have a double win, right? Setting the pointer to 0 is work, and running the destructor is work. If we could not do either of them, then all we need to do is move a bunch of bytes, which we have memcopy, which does that really nicely.
Yep. And you don't have to go back and touch it again. So if you're doing this over a whole array of things, as Vector does, you might even get some cache benefits from not having to go back and touch everything the second time. So,
okay.
Yeah.
Okay. So this is a cool idea. How do we solve it? What do we do?
Well, so I have this paper that I've been working on that I hope will get presented at San Diego, although I won't be there, so I'm looking for a shepherd. And the paper number is P1144. It's not in a publication yet. It'll be in the pre-meeting mailing. But the idea is...
We have a link to your blog post where you referenced a draft of the paper, and we have that in the show.
And the current draft is also sort of publicly available. It's on my website. It's pretty easy to find. But yeah, the blog post links to a snapshot in time of what the draft was when the blog post was in. Basically it has, I guess, at least 2 parts, maybe 3 or 4 parts. So it starts with the concept of trivially relocatable, right? And that's the property that we're trying to get at, this idea that you can memcopy it around in vector and it's okay. And that's the thing that's kind of fuzzy to define, but we understand intuitively what we're trying to get at least. And we can put rules that the compiler can use, inductive rules, to say, well, if unique putter has this property, then if I have a struct containing nothing but a unique putter, and a defaulted move constructor and a defaulted destructor, then it has that property. And if it has, 3 strings and an int, and a defaulted move constructor and a defaulted destructor, then it has this property, and so on.
If it follows the rule of 0.
If it follows the rule of 0, yeah.
And all of the types are trivially relocatable, then the object itself is trivially relocatable.
Right. If the bases and members have this property and you follow the rule of 0, then you have this property, and so on recursively.
Unless one of those pointers points to itself.
Unless one of the pointers points to itself.
Unless you've got a self-referencing object.
But then either you're not following the rule of 0, right? You preserve that invariant somehow.
Yeah, you better have a copy constructor for that.
Or else it's not really an invariant, and in that case, sure, it's okay. We're preserving the value of the pointer by doing the memcopy, regardless of where it points. We preserve the pointer's value. If you have some other invariant, you would write a constructor, right?
Right. Yeah.
And as soon as you do that, we stop assuming. Now you might say, well, unique putter has a move constructor and a destructor. So by this logic, unique putter would not be trivially relocatable, right? So for that, the paper proposes, although it admits that there might be other ways of doing this, but I think by far and away the cleanest way of doing this is to add an attribute. So there's an attribute that you can put on the class to say, class trivially relocatable unique putter. And that's a guarantee, that's a warrant to the compiler telling it, I guarantee that even though I've put some special member functions here, I assure you I have done the work to make sure that it is in fact trivially relocatable. And so unique putter in libc++ or in the library would have that attribute on it. And so it would magically become trivially relocatable from the compiler's point of view.
And so an attribute which were introduced in 11, syntactically, it's some tag that's within a double set of square brackets. And the semantic of it is, it's some type of optimization, which in fact the compiler can ignore. It can't change the actual meaning of the program. I
have a blog post about this too. The ignoring connection tool. And it's very hard to define what we mean by cannot affect the behavior of the program, right? I mean, one of the comments on Reddit after I did the blog post was someone said, well, if you can test for it, if there's a type trait that lets you test whether the attribute is there or not, then in what sense is it ignorable, right? You can certainly write a program that has different behavior depending on whether the attribute is there or not. But in the same way, we've got things coming like no unique address that you can put on a member to say, I don't care about this member's address, it's okay to have it overlap something else, right, which would replace the empty base optimization. Mm-hmm. And in that case, you take the size of, right, and you can observe, size of is 4 on this platform and it's 8 on that platform because it doesn't respect this attribute. Even just something as simple as
it's not really a question of whether or not the program can ignore it. It's a question of whether the compiler can ignore it. In other words, the compiler can ignore an attribute. If it generates code as if that attribute wasn't there, that has to be valid code.
Well, but anything that affects the sizes of a type or the properties of the type in any way that's observable by type traits could change my spine behavior. It could change, I could have a static assert that fails and it doesn't generate code, right? And we're definitely in that world already. I mean, some people are not, comfortable with that idea, but, attributes do have effects of some sort. Now, I agree, you shouldn't write an attribute that's like, this attribute, you put it on a variable and it adds 1 to it, or something, an increment attribute, like, right? There's some line that we shouldn't cross. But I strongly believe that this is not on the wrong side of that line.
Right. Okay, so essentially we add this attribute and we're telling the compiler for this particular object, it is safe when moving it, instead of calling the move assignment followed by a destructor, to just call memcopy. And we're warranting it.
You said when moving it, but when relocating it.
When relocating it, where the definition of relocate is a move followed by a destroy of the original.
Right. Followed immediately, right? They really have to be very, very tightly.
Yes. Right.
Yes. Yeah. This is not something that the compiler would go do on its own because it says, oh, I see you're moving out of this, and then later you destroy it. I'm just gonna, replace that whole thing. If there's side effects happening in between, then obviously we shouldn't do it. This is not something that the compiler is going to necessarily replace. This is something that a library implementer like Folly Vector or libc vector even, could, if this were standard, it could take advantage of it.
Well, you have an implementation, a proof of concept implementation that does exactly that.
Yes, I do. Would you like to tell people where it is?
Well, go ahead. You've explained that in the blog.
In the blog post, there is Matt Godbolt's Compiler Explorer, aka Godbolt. Has a whole bunch of compilers that you can run online and test, and everyone listening to this podcast already knows that. But one of these compilers, as of a month or two ago, is called Experimental P1144. And it's a branch of Clang that I maintain, such as it is. And it also has a branch of libc that it uses instead of the standard libc. And in this branch of the library, I've got the type traits, std is trivially relocatable and is no-throw relocatable, and so on. I've got a new standard algorithm called std uninitialized relocate that actually performs this operation. So it's sort of a combination of uninitialized move and destroy together. And again, has better cache effects, right? Because it only does one pass instead of two passes. And then in all of the containers and all of the algorithms, it has an optimized swap that says if the T, whatever I'm swapping, if it's trivially relocatable, I don't have to do move, destroy. I can actually do memcopy, and it will.
And of course, the test itself is also done at compile time.
Right, and this is all done through constraints. Yeah.
All right. And what kind of numbers did you get from your benchmarking? I mean, what are we looking at?
Well, from the benchmark I presented in Aspen at C++ Now, that was benchmarking vector reserve. So basically, I made a big vector of like 10,000 elements, and then reserved exactly 10,000 elements, put 10,000 elements in it, and then resized it to 10,001. So that caused a reallocation. And by doing this optimization, we saw basically a 3x speed up in that vector resize.
Right, and that's already in a situation where it's doing moves.
Yes,
that's on top. That's not on top of C++98. That's on top of a move-enabled solution.
Right. Now the caveat there, of course, is that you really only do this resizing of a vector geometrically infrequently. But let's say now this is now you might say, what about my now that I've done the libc++ patch, what do my benchmarks look like? And the answer is I haven't run any lately. But one that would, I think, be very interesting to run would be a sort of a big array of trivially relocatable types with maybe some unique quitters in them, where sort does a whole lot of swapping. And swapping can be done in this optimized way by memcopy. And so doing a whole bunch of them should give really good benchmark numbers. And I wish I had them today.
Yeah. All right. So you made reference to this earlier, but Howard is essentially the architect, or perhaps one of the architects, of move semantics. So Howard, what do you think of this idea of trivially relocatable as this optimization?
It's about time. What took you so long? We've been waiting for this for a long time, you know. No, in the original move paper way back in 2002, so
I remember reading that
20 years ago. I talked about something called destructive move semantics, and how, you know, even back then we realized that this was something that a lot of people need to do. We knew that Vector could make use of it during the buffer reallocation. We didn't have a good way to solve it. And what Arthur has done is say, okay, maybe we don't have a general solution for all object types, but for those where you can replace the destructive move with just a mem copy, here's how to do it. And I think this is a really nice way to carve out another significant performance enhancement.
And I just want to throw in there, as long as we're crediting the pioneers of it, that this paper is not based on Pablo Halpern's destructive move papers, but if you go back and read his papers, which I did after I had already started, writing out this one, it's almost identical. I mean, the idea of we need an operation with a name, and we need an algorithm that performs it, and we need a type trait that detects the possibility of performing it. You know, he called it destructive move, and he had std is destructive movable and uninitialized destructive move. And, and I just used the word relocatable instead because that's what Folly and EASTL do. But, you know, he tried and he failed because we don't have it. And I think it was related to the object lifetime issues, which I have not really solved either. But I'm trying to separate it cleanly from this idea of you know, there's going to have to be some sort of magic that lets us get away with skipping the constructor and skipping the destructor. And I don't want to propose that magic myself. I want to leave that to someone else.
I think you may be better off not proposing it, because we already have what's it called, placement destructor, you know, where you destruct stuff manually. We already have that. And it's existing practice that you can't use that on scoped objects, on stack objects. So trivially relocating something is just the same thing as, you know, it's the exact same restrictions. You can only use it in places where you might be able to use a manual destructor call.
Well, if you're going through the algorithm, through the uninitialized relocate algorithm, then I think I agree with you.
Yeah.
But there are libraries like Folly that just do a strict memcopy, which is totally undefined behavior. But I mean, it works, but it's undefined behavior. And this paper does not make that any less undefined behavior. No. But it really helps them with the type trait to detect when it will be okay to do it, even though it's undefined. It's really hard to talk about this stuff.
Right, but I imagine, I haven't looked at Folly, but I imagine they're mem copying from one dynamically allocated buffer to another.
Yes.
And so that is the exact scenario where if you weren't mem copying, you'd be going in and manually calling destruct on each member of that dynamically allocated array. That's right. What Vector does today.
You'd also do a move construct to create the other one.
Right. So you move construct followed by destruct.
Right. But you would actually be calling the constructor and destruct. So the object lifetime would be, you know, yes. There is a constructor called, there is a destructor called. And so what Arthur's saying is we're cheating here because we are creating objects without calling their constructor, and we're destroying objects without calling their destructor. And
absolutely. My only point is we don't have to involve the compiler because the compiler is not involved in the original problem.
But aren't there situations where that's what we're doing essentially, is telling the compiler, you can do this? We're telling the compiler, you don't need to call the destructor. I've told you that this is a, I mean, maybe I misunderstood where the optimization is coming from.
John, we're telling the library, really. This is a purely library optimization. The compiler understands how to do this inductive propagating of, when you inherit from utility, But as far as who's going to use, inside vector, inside swap, these are all library things doing this.
So in other words, if I were doing a move, say, let's say I'm returning something from a function, the compiler is not going to take advantage of this particular optimization itself.
My paper does not propose that the compiler take advantage of it at all. Now it could. It seems kind of tempting to say, that's exactly the sort of situation where you're doing a move and a destroy. And it's true.
I guess I was jumping ahead. I was assuming that's exactly what we were doing. I mean, I understand you're saying that for things like vector resize or pushback, that you're allowing the library to do that. But I also assumed, well, the compiler's going to take advantage of this too. But you're saying we don't need that. We get a lot of benefit. We get a lot of bang for this even without the compiler doing that.
We definitely got a lot of bang for our buck without doing that. And the main reason that I haven't really pursued doing that is because I really think that this needs an implementation, like the one on Godbolt, where people can play around with it. And I am qualified to write the implementation that I have written. I am definitely not qualified to try to say, when you return a value from a function, to go into Clang and find, where it does the move initialization and change that to do.
So you want users to play with the proposal before we actually standardize it? That's pretty radical.
They can play with the camel's nose. They can play with the whole camel. Whatever they want.
Yeah, I think this is a great approach. I mean, part of the reason we didn't do destructive move, 20 years ago is because it would have just been too much. You get something standardized so that future developers and researchers can build upon your work, as opposed to do the whole enchilada all at once.
Sure.
Try to do the whole thing at once, and it just collapses under its own weight. Never makes forward progress.
Well, you also terrify people because you're trying to bite off too much.
Exactly.
If you can say, this is what we're doing.
Absolutely.
And which is kind of what Arthur's doing, saying, well, we're not having the compiler will do that. We're just saying it's okay for the library to do that. But actually, from my point of view, that's actually kind of scarier, because if the compiler is doing it, the compiler is allowed to do basically whatever it wants to do. If the library is doing it, then we actually do have to think about, well, what are we saying about object lifetimes if we're saying, well, it's not.
Well, this is where you come in, John. After Arthur gets this standardized, you take the next step. You carry the torch.
Now, I will point out that in my current wording, I mean, the wording is very fuzzy, and I don't mean that it's bad wording. I just mean that it's very fuzzy wording, because the C++ standard doesn't really talk about the compiler and the library as separate entities, right? It talks about the implementation. And so what the wording currently says in my proposal is just when a type is trivially relocatable, the implementation can take the move and destroy, can take the relocation operations wherever they exist and replace them with memcopy. And it doesn't, it has that latitude. It doesn't say that it has to do it. It's not guaranteed to do it. And that means that this would not break any existing implementations, right? The fact that libc++ vector today doesn't do it, doesn't break anything, it's still conforming. The fact that std function is not trivially relocatable doesn't break anything. It's not required to be trivially relocatable. And now there's a type trait you can test, whether to see whether it is or not. But this means that, I guess, technically, that the compiler could replace a return of a unique putter, with a memcopy or something like that, without actually running the move constructor and the destructor. But the thing is, it already does that, right? I mean, under the as-if rule, you can already do that.
Well, if the compiler has, if you'll pardon me, unique knowledge about unique pointer, right? I mean, it has to know something about it. Now, if everything's inline, which of course unique pointer is, then I guess it can probably deduce that. But it's not doing it because it sees, oh, here's this type that has this behavior. It's doing it because it's looking at what it's actually going to generate and optimizing that away.
Right.
It would be tough for a compiler to do it because it's saying, oh, here's a non-trivial member function and here's another non-trivial function, and it's got to realize that the combination of those is trivial.
Well, I think in the case
but
of
if it's generating
with returning a single unique footer by value, I think compilers generally do that. I mean, they don't compilers generally will generate perfect code today for returning a single object. But as I showed in my C++ Now talk, if they generated perfect code for vector resizing of unique footers, my benchmark would not have showed a 3x speedup, right? Sure. So I am focusing on the library stuff also because I think that's where the benefit lies. But I don't know because I haven't done the implementation because I'm not qualified to do the implementation of the return or wherever else you could put this in.
Yeah. Plus, you're competing with copy and move Elijah with the return statement, where we're already doing, pretty good, especially with Richard's latest work in 17. It's very nice.
And as you know, I have another paper coming, fixing it even further. Get rid of some more copies.
What paper is that?
That's P1155, more implicit moves. And it's closely related to another paper by David Stone, whose number I don't know.
What? Oh, you don't have all the paper numbers memorized?
That's right. I'd already forgotten. You taught me something new about the language just a couple of nights ago. I didn't realize.
Yep.
Thank you again.
There are all sorts of cases. This is where you say return, X, semicolon. So it's just return and the name of a variable. We've sort of trained ourselves, especially in 17, but even in 11, we sort of trained ourselves to think of that as copulation. And even when it's not copulation, at least it will be cheap because it will do a move. And so what my 1155 does is it identifies 4 cases, which are relatively common, where the move doesn't happen and actually makes a copy, and says, why don't we just not do that? Why don't we do the move?
Talking of proposals, how does your trivially relocatable proposal relate to Niall Douglas's move relocates? That's P1029 for those keeping score.
Well, it competes with it. One of them will forestall the other, I think. I mean, Niall is interested in this relocation thing more for that aspect we were just talking about of not just the compiler being able to optimize when you say return, maybe it will do a memcopy instead. But if I have a small type that is trivially relocatable, such as unique footer or exception footer, or a struct containing an exception footer, which is why Niall's interested in it, then not only can I relocate it around via memcopy, but he's saying, well, if it fits in a register, why don't I just put it in a register? And I return an exception footer in a register. And my 1144 trivially relocatable does not do that at all. It does not change ABI on purpose, because that would break the world. But he's particularly interested in it for that reason, because it relates to this error handling, the static exceptions or herpceptions that Herb Sutter and Niall are working on. That they need some way of returning non-trivial objects in registers. And it turns out that the conditions under which this is somewhat safe are almost the same as the conditions for trivially relocatable. So they
All
want to
right,
make
so I can't keep both of these in my head at the same time. So I'm going to ask you to steer me through this. Is your proposal going to make what they're trying to do harder? Or, I mean, you're saying that one is likely to forestall the other, but why can they not be merged in some way? I mean, I understand you're trying to stay away from the ABI and ABI change, and they want the ABI change, but is this really an either or is there a way to steer something that we can have what we want?
Both proposals, as they stand at the moment, are they're proposing very similar things, and they're both proposing to add an attribute with different names, right? So if we couldn't take them both in their current form, because we'd end up with, you'd be marking your class as trivially relocatable and also as Heap relocates, and I want to try to minimize the number of concepts if possible, and I'm doing that by throwing all of Niall's concepts out, right?
Well, that's one approach.
But for the ABI issue, the things he wants out of the ABI to be able to pass things in registers are actually very close to something that already exists today in Clang. Clang has a vendor-specific attribute called trivial ABI, which relates to the Itanium ABI and makes types sort of appear to the ABI to be trivially copyable, which means they can be passed in registers, even though they're not. And so the compiler takes responsibility for still calling the move constructor and calling the destructor at appropriate times, or the copy constructor. But it changes the ABI so that instead of being passed on the stack, these objects are actually passed in registers, so they haven't got an address. And so and I have a blog post also on Trivial ABI, or Trivial ABI 101, that shows some example code gen of what that looks like. And obviously from the name, that changes the ABI. You couldn't put this on, unique putter and then, compile and link your code with a shared object that used the old ABI. It wouldn't work. But you could put this on your own types. And then you could pass them in registers.
So this never occurred to me before, but I guess I'm figuring out that what you're skirting around, because you're assuming I already understand it, which I didn't, but now maybe I do. If something's in a register, you can't call a member function on that because a member function has to have a this pointer and the register doesn't have an address. So the compiler could generate a completely different version of the function for use in situations where the object was in a register. But that seems...
That's not really what it does. It doesn't really generate a different version of the function. What it does is what it would do in that case, and you'll see this inside the body of a function. If I have a local variable of type unique putter, that can totally go in a register, right? The compiler does not make a stack frame for every unique putter in my program because it can do all of the as-if optimizations and it knows exactly what's going on. But as soon as you cross the function boundary, it has to spill that unique putter into somewhere that everyone agrees that, when the constructor of that object is called, it gets some this pointer, and when the destructor is called, it gets some this pointer, and those need to match. By definition, it's the same object, it has to have the same address. So Trivial ABI basically gets rid of that constraint and says, you know what, it's okay if you construct the object over here, and then after it's been constructed, we're going to stick it in a register and we're going to move it around, and then later we're going to need to destruct it. So we need to call its destructor, and we need to give it a this pointer. So what we're going to do is we're going to spill it to the stack over here, which might be a totally different address, and we're going to call the destructor with that this pointer. And because it has been marked with this attribute, the user is warranting to the compiler that this is okay. Constructing and destructing with different this pointers is okay. And of course, that's not always okay. But with the attribute, we're telling the compiler it is.
And that's not exactly the same thing you're saying, because all you're saying is that if you are trying to do a relocate, which is a move followed by a destruction, then that can be implemented by just moving the bytes. So it's related. It's not exactly the same thing.
I would say I mean, everything's related. Everything in the universe is one, right?
But is it trivially related?
No, it is non-trivially related. Because in the context of the relocation operation from my paper, that operation has a source and a destination, right? And they are different places. And we're taking something from the source that we constructed at the source, and we're going to do something tantamount to a move construct, which gets a source and a destination, followed by a destroy of the source. And then later, we're going to destroy the destination. And all we're doing is getting rid of that construct and that destroy and replacing that with an memcopy. But we still have the two ends being the same, that we constructed the source object and we're destroying the destination object. And they are different objects. It's totally fine for them to have different dispointers for different objects. Does that make sense?
Right. But what he's wanting to do, excuse me.
What he's wanting to do is kind of have the source object over here, and then later have the source object over here.
Right.
Okay? And that's very different from having a destination object.
And there's no particular operation in the code that does that. It's just that the compiler wants to do that for some optimization purpose. It wants to stick it in a register and then spill it back to the stack at some point.
Yes.
Is there any situation where that would not be safe to do for a type that is trivially relocatable?
I don't think so. I think it would always be safe by definition. But it's a very different sort of model.
It is a different model, but it seems pretty related to me. It seems more than trivially related.
So that operation is safe, that you can take this object and sort of relocate it around. But the practical use that you would make of that is to change the ABI of functions that return objects of this type, right?
So I think what you're saying is you want to apply your attribute to existing types.
Right. My thing, you could
without changing the ABI
at all.
So if there was a way of having your attribute with a refinement, maybe the parameter to that attribute that also gives you the ABI change, would that be a way to merge the two proposals potentially?
Yes. Although, the point of my bringing up the existing trivial ABI attribute is that it effectively is that orthogonal piece, right? In fact, today, you can mark things as trivial ABI without trivially relocatable. And that means the compiler can return them in registers, but vector and swap and so on won't actually do the memcopy optimization. I'm not sure why you want that.
I was going to say, is there actually any value in that, or is that just because it happens to have been defined that way?
It would let you do things like if you really wanted to instrument your move constructor and your destructor to printf, printf I'm being move constructed, printf I'm being destructed, right? Which we all have done, right? Trivial ABI would not remove any of those printfs. It would have to do all of those printfs because trivial ABI is not about skipping construction and destruction. It's just about the ABI change. And whereas trivial relocation is all about skipping constructors and destructors, but no ABI change. And so we already, basically, if you go play with my compiler explorer patch, you can actually try combining those two, see how they work together or orthogonally.
Right. So two possible ways forward to not lose the benefit of what Niall's going for is have a refinement on your attribute that allows you to additionally specify the ABI change, or have it a completely orthogonal concept which doesn't include the actual moving part. Is that where we're at?
And that second approach, Clang does that in practice because they already have that attribute.
Right.
Now, GCC doesn't have that attribute, as far as I know. I don't know if they're working on it.
It also doesn't have your experimental implementation.
Yes, and Clang Trunk doesn't have my experimental implementation either. It's a branch, and I hope it gets merged. I've made a pull request for it, and it's gotten very good feedback. It got a lot better thanks to Nicholas Lesser. Gave some really good feedback. shorter. But I'm not terribly hopeful of it getting into trunk unless the proposal starts making progress and it starts looking like, okay, to be standard conforming, we need to have this in trunk. That would be cool. So I had one other topic related to relocation that I wanted to make sure that we covered because I think it's important to publicize. And that is the relationship between this relocation concept and persistence or sharing, as you see in boost interprocess. Because a lot of people, I think, when they hear about this trivially relocatable concept, think that it's going to help with sharing between processes. And I want to squash that. So the use case that a lot of people have, especially if you're in the audience for a lot of Bob Stiegel's talks on fancy pointers, you know, the use case is often that you have two processes running, maybe like a producer and a consumer or something, and they're sharing a chunk of memory between them in a shared memory block, which of course, you know, standard C++ doesn't know anything about. And you want to be able to have non-trivial data structures in that shared memory. But the base address of that memory could be different in process A and process B. So process A sees the chunk of memory starting at 0x1000, and the other one sees it starting at 2000, right? And so that means that you can't put pointers, native pointers, into that memory block. Like you can't put a vector in that memory block because its pointer would have to be like, you know, 1017, which would work fine in process A, but in process B, it would follow that pointer 1017 and it would point outside the block because the base address in process B was to 2000. Does that make sense so far?
Makes sense to me.
What you're saying is that the heap allocation addresses on the two processes are going to be different. The addresses are going to be different, right? I mean, if vector says I want to allocate a chunk of memory, it depends on what process it's running in, what its pointer value pointing to that chunk of memory is going to be.
Right. Even if the allocation is done from a heap that lives in the shared memory,
right,
the addresses of the shared memory look different to the two different sides. And so boost interprocess has a very very mature way of dealing with this, which is they have this thing called offset putter that behaves just like a native pointer, but it's actually represented internally as an integer. In its body, it holds an integer. And every time you call operator star on it, you know, that's an overloaded operator that goes and takes the address of the offset putter and adds the offset, adds that integer to it, and sort of jumps up to where it was pointing to. And that operation works the same whether you're in process A, when the pointer is at 1000, and you add 17 and you get 1017, or if you're in process B and the pointer, this pointer is actually 2000, but you add 17, you get 2017. That's what you wanted. So it's a way of sharing a single data structure that appears simultaneously to have two different addresses depending on who's looking at it. And similarly, even in one process, you could say, I have this chunk of memory holding an interprocess vector using these offset putters, and everything is inside this one region of memory. And then I can serialize this whole thing down to disk and bring it all back at some other offset, or just memcopy it from one offset to the other, or use realloc to wormhole it from one offset to the other. And then I can use it over here at that new base address, and it will still work great. Does that make sense?
Mm-hmm.
And so people
feels like I want to standardize this offset pointer concept, but call it a Schrodinger pointer.
It's a relative pointer, yeah. And so people who are working in that space, which also includes people who are working on heterogeneous computing, if you're between a CPU and a GPU, or sharing stuff between a CPU and a GPU, I think a lot of them hear about this trivially relocatable idea and they say, oh, it's safe to memcopy it, right? It's safe to memcopy it from one place to the other. So I could, use this to get stuff from a CPU to a GPU by memcopying. Or I could use this to share, between two processes or something like that. And unfortunately, that is not true, right? Because our canonical example of a relocatable type, a trivially relocatable type, was something like, std vector with the default allocator, because it's just a pointer and a couple of integers, and I can move it around. But of course, if I try to do, that's our canonical example of something you can't share between two processes, or you can't just serialize its contents to disk and read them back later and expect to have a working vector, right? So there's this other concept that these people want, and I have no theory to really explain how to get what they want. Mm-hmm. But trivially relocatable does not help with those scenarios.
All right. Well, we will be watching with interest to see what kind of excitement happens in San Diego relative to this proposal. You do have someone who's going to be looking at it, or you're looking for someone to be a shepherd, you said, but is there, what's the state?
Well, I'm not going to be there because I'm going to be in New York. But yeah, if someone out there in Radio Land is interested in contributing to or benchmarking or shepherding, especially at San Diego, this paper, please send me an email or get in touch on Slack or something like that. Because this paper can definitely use all the help it can get. I hear that San Diego is officially the last meeting where sort of feature changes are going to be considered, which I find that real hard to believe, given that there's huge swaths of stuff that isn't in the draft yet. But if that's true, then the stakes are high, and I am not going to be there. So
likely to be a bloodbath.
So if people think this is a good idea, someone should help me out.
Who wants to relocate in San Diego?
There you go. All right. Well, our time has slipped away from us. I've enjoyed this a lot. I always enjoy talking to both of you because we're both in the Bay Area. I get to talk to Arthur every once in a while. I don't get to talk to Howard very much, but that's always a delightful treat. And I've got so many things I want to talk to both of you about. I wanted to ask, well, I won't even ask the question because then we'll go down that. So we need to stop. Is there anything else that we need to say before we wish everybody safe coding, Phil?
Not that I can think of. I think we covered the important points from my perspective.
All right. Howard, did you have anything you wanted to say before we sign off?
Sure. Thank you for having me.
Oh, it's great. Always great. And Arthur, other than your plea for a shepherd?
Yes, thank you for having me. And, West Const, that's all.
Oh, it hurts so much. We hates it.
If we'd known before we invited him on.
All right. I think Niall's proposals sounding better and better every moment.
Yeah.
All right. Well, please join me in wishing all our viewers and listeners safe coding. So everybody, until our next episode, safe coding.
Safe coding.